Hey guys, in this video we're going to learn about tangent lines. So we're going to talk about what a tangent line is, what's special about it. I got some notes for you, I got some examples, all kinds of good stuff. So we're going to start with what is a tangent line? So let's take some line or line segment like this, line segment, and a circle, like my daughter's frisbee that was in the backyard. And if this is a circle, and I want this to be a tangent line, then that tangent line's got to touch that circle at one point and then keep going. So this is what a tangent line looks like on a circle. It touches it at one point, called the point of tangency, and then it keeps going. So it doesn't go through the circle like that. That's called a secant line. We're not doing secant lines. And it doesn't just totally not touch the circle. It touches at exactly one point on the circle, and then it keeps going. Alright, so it has one point of tangency, and we'll learn some special properties, some special things that happen at that point of tangency, but that's what a tangent line is. Touches the circle once, and then keeps on going. Alright, we use tangent lines a lot in calculus when we talk about instantaneous rates of change. So tangent lines are important in your future. But for right now, we're just dealing with touches a circle one time. Okay, so I'm gonna go around and look for more stuff that I can make tangent lines out of. And let's go. All right, so here's the aftermath of my daughter's lunch. Here's her plate where her peanut butter and jelly sandwich once was, and the knife that was used to spread her peanut butter and probably jelly too at some point. But check it out! It's a circle. And that knife looks like a tangent line! It's a tangent line in the wild. It's a roll of duct tape as a circle, obviously, duh. And a caulk gun that is forming a tangent with it. Wow. Tangent lines are everywhere! And here's my daughter's bicycle. And look! Her wheel is a tangent. Oh no, her wheel is a circle.
You taking a video of my bike?
Oh no! Busted! So if her wheel is a circle, and then that pump down there is a line segment, and they're touching at the one point, Reagan, you're in the way.
Well, you better not be taking a video of my bike. Take a picture of Sadie.
You got jelly on her face, nerd. And then it's a tangent line. Meanwhile,
circle, like that. And this line right there, that's the symbol for tangent.
a what?
A tangent.
Yay! Say tangents are everywhere.
Tangents are everywhere.
Yeah, but say it to where people can understand it. Tangents are everywhere.
Tangents are everywhere. Tangents.
So as you can see, tangents are everywhere, and if a 6-year-old can do it, you can do it too. She can kind of do it. Alrighty guys, real quick I'm going to go through our notes and talk to you about tangent lines. We've already kind of talked about them in the little introduction, but I just thought I'd kind of read your notes out loud and help you make sense of them. So what the heck is a tangent line? Well, LP over here is a tangent line. It's tangent because it touches the circle O at exactly one point, point P, which we call the point of tangency. So point P is called a point of tangency. Alrighty, so tangents are important in calculus. We use them a lot. We always talk about the tangent line, slope of a tangent line. So for calculus, it's a big important thing. I don't really know what else it would be important for. But anywho, for us, it's kind of a big deal. And what is it? It intersects, in this case, a circle at exactly one point. So it does not, what it is not, is it's not something that's going through the circle and intersecting at 2 points. We call that a secant. Okay? It doesn't just completely miss the circle. Nope. It hits it at exactly 1 point, okay? So that is what a tangent line is. All right, we got 3 theorems about tangent lines. This first one's probably the most important. It says if I've got a tangent line, hey, I know that AB is a tangent line. Somebody really smart told me that AB is a tangent line. Has a point of tangency at P. Well, if that's true, if AB is really a tangent line, then it's going to intersect this radius right here. So I've got a radius and a tangent line. And what's cool about those things is they intersect at a right angle, always. The tangent and the radius have a special relationship. They are perpendicular to each other. That's the symbol for perpendicular. They're perpendicular, which means they make a 90-degree angle when they intersect. So AB's a tangent line. CP's a radius, then those dudes make that 90-degree angle because they're perpendicular to each other. Cool, 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 cool. Let's look at the converse, which means flip it around. Conversely, if these two segments, if AB, which I don't know if it's a tangent or not sure yet, and CP, which is a radius, if those happen to make a 90-degree angle, well then AB must be a tangent. So it's the converse. It's saying, hey, they make a 90-degree angle, therefore, AB must be the tangent line. It sounds very similar to the last theorem. It's just the converse. We just kind of reversed it. So if that right angle's there, then AB must be a tangent line. And lastly, if I've got 2 tangents, like Mr. AB over here and Mrs. AC, and they're meeting up, ooh, romantic, they're meeting up at a common endpoint at A, then those two must be congruent to each other. So whenever 2 tangents meet up at a common endpoint like A here, then they're going to be congruent to each other. So the length of AB is going to be the same as the length of AC. So in one of the other examples, I prove it and all that good stuff. So there's our notes. I hope you learned something. And my daughter's singing. All right, guys. Watch the rest of the videos, answer the quizzes, make good grades. See ya.